Welcome to Appendix A3. So now we're going to look at polynomials. So in this appendix, we'll define a monomial, a polynomial. We'll take special products of polynomials. We'll use regular old long division to divide polynomials and find remainders. We'll factor polynomials and we'll complete the square. The completion of the square sort of in preparation for deriving the quadratic equation. So a bunch of vocabulary initially in the form of a definition. A monomial is a monomial in one variable is the product of a constant and a variable raised to a non-negative integer power. So a monomial of the form a x to the k, where a is a constant, x is the variable, and k is the non-negative integer, is an example of such a monomial, and a constant a is called the coefficient. If a is non-zero, then k is the degree of the monomial. If you have x to the 0 power, then that's going to produce a constant function if we treat them as functions, and ultimately we will, and we'll consider polynomial functions. Then that's still falls in the category of a monomial. For our purposes of dealing with polynomials, though, constant functions are something that we might not spend a lot of time on in the setting of polynomials. But a constant is certainly a legitimate form of a monomial. Parameter k is called the degree of the monomial. So that being said, if k is 0, then we have a constant monomial. The sum or difference of two monomials having different degrees is called a binomial. Of course, you're familiar with binomials, I suspect, and raising them to powers, as we'll see in this section. The sum or difference of three monomials with three different degrees is called a trinomial. A little impressed if you've heard of that before. We're not going to spend much time with trinomials. We'll probably encounter some along the way, but this is likely the last time we'll use that term trinomial. Binomials, big deal. We'll spend a fair amount of time on binomials, and monomials are simply the things that make up polynomials. So that's how all the verbiage fits together. A polynomial in one variable, and this is a bit more to our interests, is an algebraic expression of the form a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, dot, 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 a sub 2, x squared, plus a sub 1x, plus a sub 0. So this is a polynomial. We will spend a good deal of time on polynomial functions. The subscripts simply indicate that these coefficients are potentially different. an minus 1 down to a sub 0. They're constants. They're called the coefficients of the polynomial. X is the variable. N, the degree of that polynomial, as we'll define it down here, is greater than or equal to 0. If n equals 0, we're actually dealing with a constant term and a single term. And the pattern is the subscript on the a matches the exponent on the variable x. So we have a sub n, x to the n, and then the exponents decrease until we get down to x to the 1 and x to the 0, which we don't write. The a sub n, x to the n is called the leading term. With that verbiage, then it's preferable to write a polynomial in decreasing powers of x, highest power of x on the left and constant term on the right, or at least the smallest power of x on the right. Not required, but it's certainly motivated by the terminology, and that's how we'll often present these. So habitually, that's how we'll do it. I would kindly request you write your polynomials in decreasing powers of x as well, just so we're on the same page notationally. The monomials that make up a polynomial are called its terms. If all the coefficients are 0, then the polynomial is called the zero polynomial, for which the degree is not defined. in some settings, 0 doesn't even count as a polynomial. The reasons for that are related to the fundamental theorem of algebra, which we'll encounter along our way. An n-degree polynomial has, if you use complex numbers, has n roots or n zeros, n numbers that make that polynomial take on the value 0. But then that doesn't work for the 0 polynomial because it's 0 all the time. So everything is a root of the 0 polynomial. So just be careful out there. This won't have much of an effect on us in practice, but in your future travels, you may take classes where the 0 polynomial doesn't even count as a polynomial. In a modern algebra class, that would likely be the case. Polynomials are usually written in standard form, beginning with the non-zero term of highest degree and continuing with the terms in descending order according to degree, like written up here, like I suggested earlier. So I recommend you write polynomials in standard form, just so we're on the same page, just to keep some things consistent and streamlined. Let's look at an example. Notes from this section. Tell whether this thing is a monomial. If it is, name the variable and the coefficient and give the degree of the monomial. If it's not a monomial, state why. It's not a monomial. A monomial was a number times the power of x. And this is more than that. Actually, it's 2 monomials. This is actually a binomial. The expression 3x squared plus 4 is not a monomial. It's a binomial. It's a sum of the 2 monomials, 3x squared and the monomial 4. This counts as a monomial. It's a constant. Think of it as 4x to the 0. Looking at monomials, we've answered their question, but let's get a little more mileage out of this. The monomial 3x squared, that's degree 2, the power of x, the coefficient is 3, and the variable is x itself. Here, the coefficient is 4, the degree is 0, 4x to the 0, you'd interpret it as, and again, we could think of x as the variable. Back to the notes. Okay, so mostly what we've done so far in this section is just terminology. Let's do some algebra now. You might recall FOIL, the FOIL method of multiplying together binomials from high school. It involves the product of 2 binomials, can be illustrated as follows. This is an image from the textbook. It's called FOIL because it deals with the first, the outer, the inner, and the last. And it's really just distribution. So if we have ax plus b times cx plus d, so both of these are binomials, multiplying together 2 binomials, special case, they're both first degree polynomials. It's a product of 2 first degree polynomials. One way to deal with it is to distribute this product over this addition. So we would have ax times cx plus d, ax times cx plus d, plus b times cx plus d, plus b times cx plus d. So that's an application of distribution. Let's do another application of distribution. We'd have ax times cx, ax times cx, ax times d, and distribute over here to get b times cx plus b times d, and that's the last 2 terms. Let's simplify it a little bit. They've used the dots to indicate the most recent act of multiplication, is how they've broken these up in this particular line. But that gives us acx squared, collecting the x's together. Here we've got adx, moving the x to the right. Here we've got bcx, moving the x to the right. Just got bd there. We could go one step further and factor the x out of this center term to get an x squared term, an x term, and a constant term. Now, the reason this is called FOIL is, to back up to this previous line, we've got a first and a last in each of these two expressions. AX is first in this expression, CX is first in that expression. D is last and B is last. And they've labeled these also inner and outer. So they're treating A of X, A times X and D as outer. They're the outermost in the little list. And the inner pair is the B and the CX. So that's the terminology being used. And FOIL fits into this because when you multiply out, forget all the distribution stuff. That's where it comes from. But what it results in is a product of the first, the outer, the inner, and the last. FOIL, first being this one and this one. These are the two firsts, as it says. AX times CX, AX times CX. We got it from the distribution. Outer would be the outermost as it's written. AX and D, AX and D. The inner are the two closest to each other between the parenthetic expressions. B and CX, B and CX. And last is the product of the two last ones per binomial. So the B and the D are the last in each, and that produces the product BD, and we've already factored it. So a common mistake is to simply multiply the first two things together and the second two things together. It doesn't work like that. Distribution applies, and to multiply two binomials, you must FOIL them. So let's look at a couple examples of that. Okay, multiply out number 48, this binomial and that binomial, or these two binomials and these two binomials. So two problems. First, number 48, we're going to multiply 3x plus 1 times 2x plus 1. Let me very specifically follow the FOIL idea. The textbook uses little dots quite often. I've used parentheses to isolate pieces. So we should have first. This should be the firsts. 3x is first, 2x is first, the product of the firsts, plus outer. The outer are the 3x and the 1, 3x times 1. Inner, be these two closest together, be the 1 and the 2x, a 1 and a 2x. And the last one, last in each of those, 1 times 1. I've preserved the order on these. I presented them in the FOIL order when first encountering this. I'd highly recommend you do the same thing. And I could treat the product of the first as 2x times 3x and write it in the opposite order, but that doesn't help any. It's not wrong, but it doesn't help any. So following the FOIL pattern, we get exactly this. 2x and 3x give 6x squared. Here's a 3x and a 2x, a 3x and a 2x, and 1 times 1 is 1. Collect together the common powers of x that will result. They always result from the outer and the inner in this situation. And that gives us 6x squared plus 5x plus 1. If this is a problem for you, you need to spend some time on this and work some examples, because this is pretty basic background stuff for Precalculus 1. Let's do another one. All right, same idea. This one's going to simplify a little bit more. We're foreshadowing a little something with this particular example. First, x times x, x times x. Outer, x times 1, x times 1. Inner, this times that, negative 1 times x. Notice the negative carries along with it. Negative 1 times x. Last, negative 1 and 1. The negative carries along, negative 1 and 1. There you go, it's been FOILed. Let's simplify. X times x is x squared. X times 1 is x. Negative 1 times x is minus x. Negative 1 times 1 is negative 1. Here's what we get. Oh, the plus x and minus x, those cancel out, and we're left with x squared minus 1. So the x term disappeared. This is of a very special type, as we'll see. So these often produce things of this sort. So there's a couple of examples on FOIL. Returning to the notes, we can use this FOIL idea and some related ideas to present the following. The difference of two squares. We'll take x minus a times x plus a. We'll get x squared minus a squared. We just did that. In the event that a was 1. we had x minus 1 times x plus 1, and we got x squared minus 1 squared. But if you have a difference, I might want to read this backwards, if you have a difference of two perfect squares, then it can be factored like this, and we're headed to factoring polynomials. We'll spend a pretty good amount of time factoring polynomials. It's a very common tool in precalculus. So difference of two perfect squares can be factored as this, if you like. If we were to take x plus a and square it, foiling, we'd get the first squared, we'd get the outer squared, which you would find would be x times a and a times x, as the outer and the inner, producing two ax's. And then we get the last, which would produce a squared. So when you square this, you get x plus a squared is x squared plus 2ax plus a squared. You don't want to spend the rest of your life foiling everything by hand. This is a very, very, very useful pattern here. What we get when you square this is we get the first term squared, we get twice the product of these two terms, and then you get the last term squared. So remembering it's first squared plus twice the product plus last squared, very useful. And it comes from FOIL. You want to FOIL it, you go right ahead. You'll get the same thing if you want to do it slowly through the FOIL. But in these videos and in the classroom, we'll speed things up a little bit and take advantage of this knowledge and not go all the way back to the beginning every time. If we had x minus a squared, FOIL that, similar pattern. You get x squared minus 2ax plus a squared. So this time, the negative here produces a negative here. So we get the square of the first, the square of the last, and we get, actually we still get twice the product. The product of these two would be negative ax. We get negative 2ax, twice the product. So that pattern still holds. This stuff you need to know. The following, likely we'll look this up if we need it, dealing with cubing and factoring related to cubes. So these first two formulas, very, very essential. You need to know that. You need to have those in your head. These, be nice if you could get them in your head. I ain't that sure they're in my head. Maybe the first one is. I don't know about these last two. What we're doing here is cubing a binomial, x plus a cubed. If you multiply that out, you'll have to FOIL it twice. It'll take a little bit of time to get through that. Trust me, you get x cubed plus 3ax squared plus 3a squared x plus a cubed. Now to remember it, there's a little pattern. For one thing, the x's go x cubed, x squared, x to the 1, constant term. So this is a standard form of this polynomial. So the x's decrease in powers. The a's increase in powers. There's no a's here, a to the 0. Here's a to the 1, a to the 2, a to the 3. So while the x's decrease in powers, the a's increase in powers in standard form when read from left to right. The only other thing to remember is that you get these coefficients of 3 here. Well, it's related to the fact that you're cubing. In the previous one, you got a 2 in that center term, and it's related to the fact that you're squaring. We could look at x plus a to the 4th power. Well, it gets a little bit more involved, but it follows kind of a similar pattern to what you have here, certainly in the decreasing powers of x and the increasing powers of a. Finding these coefficients becomes a bit more complicated if we go to 4th powers or higher. It's contained in something called the binomial theorem. You'll see in calculus, and probably we'll see before we're done in Precalculus 1. If we took x minus a cubed, well, it'd be the same thing. In fact, we could take this a and replace it with a negative a. Nothing would change there. This a would become a negative a, and we'd pick up a negative sign in front of that. Right there it is. If we replace a with negative a here, well, the squaring will absorb that negative sign. That doesn't change, same term. And if you replace a with negative a in this formula, this will produce negative a negative a cubed, which is negative a cubed, it produces a negative sign. We simply got negatives in every other position in this one. If you're going to remember anything beyond the first two, possibly these are somewhat useful. The next two, I don't mind looking up if there arises the occasion that we need them, but what we're doing is dealing with the difference of two cubes, x cubed minus a cubed. And the claim is this is equivalent to x minus a times x squared plus ax plus a squared. We had a difference of two perfect squares. We factored that in the first equation. Here's how you factor the difference of two perfect cubes, x cubed and a cubed. That's true. Yeah, we could use distribution and multiply all that stuff out. And what you'd see is a bunch of the center terms cancel. And that's why this works. If we wanted to deal with factoring x cubed plus a cubed instead of minus, similar pattern. Notice we got an x plus a here, and we get a negative sign in this term. So the negative here became positive there, the positive here became negative there, and we switch this negative for positive there. This holds why? Because you multiply it out and you see that it's actually true. Use distribution, and that's how you confirm these. Not terribly interested really at all in the last two, possibly the last three. This one we're likely to use these two. If we need them, we'll probably have to look them up because we'll use them so infrequently. Let's shift gears a little bit to an idea of division. So here's an illustration with just some integers, quotients of integers. Consider the equation 842 divided by 15 equals 56 plus 2 divided by 15. You do the long division, and you find this is true. On the left-hand side, we've divided 842 by 15. The number 842 in this expression is called a dividend. The number 15 is called the divisor. So we've taken the dividend and divided it by the divisor. On the right-hand side, we see that we've expressed this quotient as an integer plus a fraction. Integer 56 is called the quotient, and here's the fraction. The number 2, in this case, the numerator, is called the remainder. So if you'll take 842 and divide it by 15, it will go in 56 times with a remainder of 2. To produce an equality between these, you need to take that remainder and divide it by the divisor of 15. What we've got then is that the dividend equals the quotient times the divisor plus the remainder. In this case, that would be 842 equals 56 times 15 plus 2. Oh, good. There it is written right there. So this is how this is expressed in terms of products and sums. All this lingo about divisors and dividends and remainders and stuff, I'm not terribly hung up on. I'll try to use the right words at the right time. But this vocabulary is not particularly essential. The division of polynomials can be dealt with in a similar way. So we'll use long division to divide one polynomial by another. We'll have a divisor, a quotient, a remainder, and the dividend. So same idea with these numbers as applied to fractions. Instead of throwing around a bunch of definitions, let's just do one and illustrate the technique of long division using fractions. So the question is, find the quotient and the remainder in the following. Check your work by showing quotient times divisor plus remainder equals dividend. So there's all those words. Divide 5x to the 4th minus x squared plus x minus 2 by x squared plus 2. Okay, usual thing, regular old division. We'll take the dividend, if I can remember all those words, and the divisor, and see how many times it goes in. We'll get the quotient up here and the remainder down here. All right, so 5x to the fourth minus x squared plus x minus 2 divided by x squared plus 2. All right. How many times does x squared plus 2 go into 5x to the fourth, the first term? 5x squared times, because 5x squared times x squared is 5x squared. I'm sorry, 5x to the fourth. We got to multiply the 5x squared times a plus 2 as well. That'll give us a 10x squared. So take this, multiply it by that to produce this polynomial. Then we'll subtract. So I put parentheses around this, next, and subtract, producing the next line. The 5x to the fourth cancel. That's the reason we multiplied by 5x squared, to get the cancellation here and something smaller. Here we'll have negative x squared minus 10x squared. Remember, we'll subtract. Negative x squared minus 10x squared produces negative 11x squared. And we'll bring down the x and we'll bring down the 2. We're dealing with a squared term and a constant term. That's the reason we brought all three of these down. Squared term and a constant term. There's an x term we'll bring down as well. Next, how many times does x squared plus 2 divide this? Well, I need a number. I need a polynomial in general, but I need a thing that, when I multiply it by this, produces this highest power of x. So we need a negative 11. Negative 11 times x squared plus 2 gives us negative 11x squared minus 22, aligning powers of x, because that's how we're going to do the arithmetic with the subtraction. So the negative 11 times this binomial produces this, excuse me, and then we'll subtract. Negative 11x squared minus negative 11x squared, 0x squared. The x is brought down, negative 2 minus, we're subtracting, negative 22 is negative 2 plus 22 yields 20, and so there's the remainder. Of course, x squared plus 2 can't divide into x plus 20. This is a first degree polynomial. That's a second degree polynomial. So the quotient is 5x squared minus 11, and the remainder is x plus 20. To check it, and it scrolls off the bottom a little bit here on my screen, but we would take the quotient times the divisor plus the remainder. Quotient, divisor, remainder. Foil this because it involves product of two binomials. Foil it, producing this. Remainder, x plus 20 is down here. Simplify, and indeed it checks. So there's all the details on the simplification on the slide and in the notes. So the arithmetic is correct. Let's do another one. Number 74, and we'll do the same technique. Long division, and then we'll check it. So this one was take x, well, let's see the statement of it. This one is to take 1 minus x squared plus x to the fourth and divide it by x squared minus x plus 1. That ain't in standard form. Let's write it in standard form when we do the computations, decreasing powers of x. So we'll write this x to the fourth minus x squared plus 1. X to the fourth minus x squared plus 1. Notice I left the little gaps in there. I left the gap where the x cubes would be. It's 0x cubes. And I left a little gap where the x's might be. So here's that fourth degree polynomial where we're dividing it by this second degree polynomial. How many times does x squared minus x plus 1 go into x to the fourth? Goes in x squared times x squared times x squared is x to the fourth. We'll do the subtraction and we'll lose that. But some other stuff happens as well. Let's see, I'll take that x squared, multiply it by the x squared here to get x to the fourth. Also got to multiply it by the negative x to get a negative x cubed, and the 1 produces the x squared. Subtract, this disappears, this becomes positive, 0 minus a negative x cubed gives us the x cubed. Negative x squared minus x squared gives us negative 2x squared. So there's the first step. Next, how many times does x squared minus x plus 1 go into x cubed? X times. We're trying to produce the x cubed term. We'll produce some other stuff, and then we'll simplify. But we'll take x next. X times this is x cubed minus x squared plus x, multiplying the divisor by x. Parentheses and then subtract is the arithmetic being done. The x cubes disappear. We get negative 2x cubed minus negative x squared. That's negative 2x squared plus x squared. So that yields a negative x squared. Here we've simply got minus x. And let's bring the 1 down. Now we're dealing with a second degree polynomial. So we'll bring down the constant of 1. How many times does x squared minus x plus 1 divide this? I want to get a negative x squared, so we'll take a negative 1 up here. Negative 1 up here times this produces a negative x squared. It also produces a plus x and a minus 1. All right. Parentheses and subtract. These are gone. We're left then with negative x minus x, negative 2x, and 1 minus negative 1. It's 1 plus 1, and 1 plus 1 is 2. So quotient is given up here, x squared plus x minus 1. Remainder is given down here, negative 2x plus 2. To check it, we take quotient times divisor plus remainder. Here you've got to multiply together two trinomials. And you got a way of doing that. Not really. We had a little formula related to the product of two binomials. We could come up with one for two trinomials as well. Probably pretty messy. Let's just distribute. Let's go through this one in its entirety. Here's what we're going to do. Let's distribute this term over the x squared, the x, and the negative 1. So we'll have x squared times this term, x squared times that term, x times that term, x times that term, and negative 1 times that term. Negative 1 times that term. And then we'll have the remainder. Let's drop the parentheses on that. Gives us a negative 2x plus 2. Now distribute. Again. Okay. X squared times each of these. Add exponents. We learned that in the previous section. This will produce an x to the 4th, a negative x cubed, and a plus x squared. X to the 4th minus x cubed plus x squared. Next distribution. This will produce an x cubed minus x squared plus x. X cubed minus x squared plus x. Distribute the negative 1. That'll give us negative x squared plus x minus 1. Negative x squared plus x minus 1. And here's the remainder part. Okay, let's collect together powers of x. And when we do, we're supposed to get this thing. X to the 4th, there's only one x to the 4th. Let's write that down, it's highest power of x. X cubes, here's a negative x cubed, here's a positive x cubed, those two cancel. And that's all the x cubes. So there's 0 x cubes, so we won't write them. X squared, positive x squared minus x squared, so those two cancel. There's another minus x squared. I think we were left with negative 1 x squared. X's. Here's a plus x. Here's another plus x, that's 2x. Minus 2x, we're back to 0x. There's no x's. Constants. Negative 1 plus 2 leaves us with positive 1. So we get x to the 4th minus x squared plus 1. That's what we were, what we were supposed to get. That was the dividend, and we've got the correct answer. So you check division with multiplication and addition when there's a remainder involved. Back to the notes. All right. We're going to discuss division backwards. We're going to discuss factoring. This is multiplication backwards. We want to take a polynomial and factor it and write it as a product of other polynomials. Let Q be a polynomial of positive degree. Let P be a polynomial whose degree is greater than or equal to the degree of Q. The remainder, after dividing P by Q, is either the zero polynomial, in which case we've got a divisor of that polynomial, or a polynomial whose degree is less than the degree of the divisor of Q. Here's what all that stuff means. If I take a 5-degree polynomial and I divide it by a 3-degree polynomial, the remainder will be of degree less than 3. So that's what this stuff is about, whose degree is less than the degree of the divisor. For example, in this last example, we took a 4th-degree polynomial and divided it by a 2nd-degree polynomial. That theorem says the remainder will be less than 2nd degree, and it was 1st degree. In the previous one, we took a 4th-degree polynomial and divided it by a 2nd-degree polynomial. Then the remainder will be less than degree 2. In fact, it was degree 1. So that's what that comment is. And that shouldn't come as a surprise to you. If I've got a degree 2 polynomial down here, well, I can do more division. I can continue on the division process until we get something of degree less than the divisor, in which case we have to stop. So that's the technique behind this theorem A.3.A, as I've labeled it. All right, like I said, we're really interested in factoring. So expressing a given polynomial as a product of other polynomials is called factoring. The other polynomials are factors of the given polynomial. The real goal usually is to find where a polynomial is 0, and you do that by factoring the polynomial. So in the long run, it's not the factoring we're interested in, it's something that we use the factoring to find, that is, roots or zeros of a polynomial. In this section, we'll consider only polynomials with integer coefficients, and the factoring problem is then called factoring over the integers. Now, there's more to life than integers, but in the following conversation, coefficients are always integers. So we'll do factoring involving integers. Not that you couldn't generalize this and do factoring involving rational numbers, for example. We can multiply out 2x plus 3 and x minus 4 to verify that what we get, foiling it, let's believe what's stated here, we'll get 2x squared minus 5x minus 12. So the factors of 2x squared minus 5x minus 12 are these two things, are 2x plus 3 and x minus 4. But at this stage, we're good at multiplying out to get other stuff. We want to go backwards, and that's a little trickier. So the plan is not to multiply out and produce a big 2nd degree polynomial, but to take a big 2nd degree polynomial and find these factors. We want to do this backwards. And there's an organized arithmetic way to do that when the coefficients are integers, which is exactly what we're dealing with. A polynomial with integer coefficients is prime if the only factors of the polynomial are 1 and negative 1, and the polynomial itself. Oh, and the negative of the polynomial. Excuse me, let me read that again. It's having a little equipment troubles there. A polynomial with integer coefficients is prime if the only factors of the polynomial are 1, negative 1, the polynomial itself, and the negative of the polynomial. So nothing divides it except maybe plus or minus itself and plus or minus 1. And these always divide any polynomial. A polynomial that's been written as a product consisting only of prime factors is said to be completely factored completely. Okay, we had some special products above. We'll go back and look at them if we need to. With that in mind, let's look at number 78. Factor completely x squared minus 9. If it can't be factored, say it's prime. And we already dealt with something like this. We did. Let's go back to the notes. So we had special products mentioned upstairs. X squared minus 9 is the question on the table. Does that look like any of these? Looks like this one. X squared minus 9. Or well, x squared minus 3 squared is what we have. So we're going to use this difference of two squares, that's what we called it, this little formula here, to factor what we have here. So difference of two squares stated what we just looked up. The right-hand side of this equation with a equals 3 gives x squared minus 9. So if you make a equals 3, this will become 9, and that's exactly what we're dealing with. So taking a equals 3 gives us x squared minus 9 equals x plus 3 times x minus 3. Take a equals 3. You want to take a equals negative 3. That'll work as well because negative 3 squared is also 9. But I just need one value. A equals 3 will work, and that tells us that x squared minus 9 factors into x minus 3 times x plus 3. End of story. It's factored completely. They're first degree polynomials. You couldn't possibly factor them anymore. Back to back to where we were. We'll see in a not too distant future that we can factor any second degree polynomial. Ax squared plus bx plus c. How do you factor that? And quadratic equation. So we're heading in the direction of the quadratic equation. That's the reason for the use of the a's, b's, and c's. Now this is going to be verbally clumsy for me because we're about to consider two different constants, lowercase a, lowercase b, lowercase c, those kinds, and a second kind, capital B and capital C. The capital letters will be composed of the lowercase letters. It's easier to read than it is to say. So what we're going to do is concentrate first on a second degree polynomial of this form. 1 x squared plus bx plus c. Maybe I should read that more carefully. 1x squared plus capital BX plus capital C. So we're considering first factoring these kinds of polynomials. And then next we'll look at something more general. Okay. We're really trying to multiply out backwards. We're trying to do FOIL backwards, or see what FOIL would imply. To factor x squared plus capital BX plus capital C, where capital B and capital C are integers by FOIL, we try to find integers, lowercase a and lowercase b, whose product is C and whose sum is B. So there's the whole story right there, written verbally. Let's write it symbolically. Symbols is what we're going to have to manipulate, so that's the way to go. That is, we need to find integers, let me just call them a and b, where capital B equals a plus b and capital C equals a times b. If you can do that, so the story symbolically becomes find lowercase a and lowercase b, it satisfies these equations. Then we'll have x squared plus bx plus c equals x plus lowercase a, x plus lowercase b. Because when you FOIL this, you'll get x times x, x squared, a times x, x times b, so it was inner and outer, that is a plus b times x, when I factor an x out, and then we'll have the product of the lasts, the ab. So we'll have x squared equals lowercase a plus b, x, plus lowercase a times b. But we're requiring a times b equals c, so we'll get a capital C there, and a plus b equals capital B. So we'll get a capital B here, we'll get a capital C in front of the AB, and that's exactly what we were looking for. X squared plus capital BX plus capital C. That's what we'll have if we can find A and B satisfying this condition. And for us, for now, everything's integers. That's going to change at some point, but for now, integers. Let's illustrate that with an example. Number 83 says factor completely x squared minus 10x plus 21. If it can be factored, it can. So I need a good example of something that we can do at this stage. Well, we're looking for lowercase a and lowercase b, such that the sum of those two numbers equals b, this coefficient here, capital B, negative 10. And the product of those two numbers equals capital C, equals 21. So we need two numbers that add together to give this and multiply together to give that. Let's start with the condition a times b equals 21. There's only a small number of ways you can write 21 as a product of integers. You could use 1 and 21, or negative 1 and negative 21. You could use 3 and 7, or negative 3 and negative 7. But I don't think that's it. So counting signs, there's 4 possibilities. 1 and 21, negative 1 and negative 21, 3 and 7, negative 3 and negative 7. So we've got those 4 possibilities. Of those 4 possibilities, does one of them involve two numbers that will sum to negative 10? This one does. Since negative 3 plus negative 7 equals negative 10, then we can take a equals negative 3 and b equals negative 7. The 1 in the 21 doesn't work. And out of that, you're going to produce, 22 or negative 22. We could interchange the negative 3 and negative 7. If I use the positives, 3s and 7s, and that's going to produce positive 10, and that's not right. So negative 3 and negative 7 is the correct answer. We'll let a be one of those and b be the other. That doesn't matter which one. So we'll take a to be negative 3 and b to be negative 7. And that gives the factors x plus a, that is x plus negative 3, x minus 3, and x plus b, x plus negative 7, or x minus 7. And so what we were given factors is this product. If you'll FOIL it to check it, it will work because we've done the arithmetic correctly. FOIL is where the a and b idea comes from. We'd have first, that'd be x squared, outer minus 7x, inner minus 3x, minus 7x minus 3x is minus 10x, center term here. And last, that'd be negative 3 times negative 7 would be positive 21 as desired. So indeed, FOIL works, and we did it correctly. If this is something that's not recently familiar to you, you need to practice these because we will be doing this kind of thing in pre-calculus. Not complicated. You have an algorithm to go through and do it as described in these notes with the a and the b, the lowercase and lowercase a and lowercase b stuff. Okay. We're here in pre-calculus 1 to consider only real numbers. My area of math is complex analysis. So I got nothing against complex numbers. I've added some sections to the notes and to the videos, time permitting, that relate to complex numbers. It's not a formal part of the class, but we're just so close to doing some really clean things. Things get cleaner, it turns out, when you look at complex numbers and you don't restrict yourself to real numbers. Okay, things may not be all that completely clean in here. The fundamental theorem of algebra, for example, requires us to talk about complex numbers. But I guess things are a touch more simple if we just stick to real numbers. We just ignore complex numbers. That'll be the content of the class, though some of the supplements will be a little more general and we'll deal with the complex numbers, usually denoted with a kind of a backbone C. So until the last section of chapter 4, section 4.6, and the 10th edition of the book at least, we'll only study real numbers. And currently chapter 4, section 6 is it's not a formal part of pre-calculus 1. I'm going to include it in the notes and videos anyhow for your education. Whenever a real number a is squared, the result's non-negative. That is, a squared is greater than or equal to 0 for all real numbers a. Complex numbers, they can behave differently, but here's our constraint. So, since we are restricting ourselves to real numbers throughout the class, though some of the supplements don't, we can say, certainly in this section, any polynomial of the form x squared plus a squared, where a is real, this is prime. This parameter here, a squared, is greater than or equal to 0. If it's strictly greater than 0, then this cannot be factored. Factoring a polynomial of second degree is equivalent to finding roots of that polynomial, and this is a polynomial function. This is never 0 if a is positive. There's nothing you can square to get a negative out to cancel with this positive term here. This never equals 0 provided a is positive, so this must be a prime polynomial. If a equals 0, then this is just an expression, the expression x squared, which can't be factored either. So the polynomial x squared plus a squared, this is a prime polynomial. It can't be factored for any real number a. Actually, this is a little bit more than we're doing in this section. In this section, we were taking the coefficients to be integers. We can actually say something about this for real numbers. One can show that every polynomial with real coefficients can be factored into prime factors, which consist of prime first-degree polynomials and prime second-degree polynomials with real coefficients. It's a shame we won't get to deal with this. It's in that section that we won't cover. So let's elaborate on that a little bit. I hand you a polynomial. Ideally, you can factor it into first-degree polynomials and second-degree polynomials, which are themselves prime. So every polynomial with real coefficients can be written as a product of, sometimes they're called linear terms, first-degree polynomials, and quadratic terms, second-degree polynomials. You will see this again. This idea pops up in Calculus 2 in a setting called partial fractions, integration by partial fractions. You'll see this. The justification of this is very easy if you'll let me use complex numbers, but I've given you the story about complex numbers as it relates to this class. So we'll take that as given. What this means is when we're factoring polynomials, we'll be stuck with some second-degree polynomials that can't be factored, some prime second-degree polynomials. And ultimately, we need to figure out why those polynomials are prime. That we haven't addressed. Well, in one special case, the x squared plus a squared case we've addressed, but we haven't addressed it in a more general setting. One trick for factoring polynomials is grouping. In this method, we recognize common factors and take advantage of the distributive law of multiplication over division. Excuse me, should read multiplication over addition. The examples we do are the examples we can do. And this isn't always laid out, honestly, in an algebra class, but there's algebra problems. It's easy to make up. They can't be solved algebraically. Well, we ain't going to do any of those. So you leave Precalculus 1, about the first half of Precalculus 1, having learned a hodgepodge of little techniques, but we never just did big, giant, general problems. Well, there's reasons for that. Some big, giant, general problems can't be done. So we're doing what we can do, and we're not doing what we can't do. So the techniques you see in here, granted, may be a little bit specialized, but there's a reason for that. To further explore those reasons, take a senior level class on Introduction to Modern Algebra, and you'll delve into the idea of algebraic solvability of equations. For us, we're about to see a technique that's actually, if it's applicable, is quite useful, and it is to completely factor this fourth degree polynomial. If it can't be factored, say it's prime. All right. This is to illustrate the grouping trick. What we're going to do is, and technique, I guess I should call it instead of trick, but it's really a trick. Take these first two terms. Let's factor out what we can from those. We could, first two terms, we could factor an x cubed out of these first two terms. That'd leave us with an x plus 1. Distribute back, we'd get x to the fourth plus x cubed. Right. Let's do that. Can't argue with the validity of it. You might argue with the motivation for it, but you can't argue with the validity of it. So we get something of this form. We get an x plus 1. Hey, there's an x plus 1 over here. It's a trick. It's a textbook example, quite literally. Well, then let's factor the x plus 1 out of these two terms. That's the idea of factoring by grouping. It's awesome when it works, but it doesn't always work. So it's something you check for when trying to factor early on. If you can do this by grouping, do it, because it's easy when it works. It just doesn't always work. We can factor the x plus 1 out of both of these, and we'll be left with an x squared term from here and a plus 1 from here. So we'll get a, x cubed term here and a plus 1 here. So we get x cubed plus 1, factoring the x plus 1 out, produces this. If you're having a little trouble seeing that, distribute it back. We'd get x plus 1 times this plus x plus 1 times that. And that's exactly what the previous expressions are. All right, so we got it factored. Can you factor x cubed plus 1? That's a sum of two cubes. We were dealing with a sum of two cubes before. We went back and looked it up previously. Let me just state it here now. We had this expression before. The expression I said, if we need it, we'll go back and look it up. Well, here it is. We saw that x cubed plus a cubed can be written in this form. So let's take advantage of that. Arguably another trick. X cubed plus 1 equals this if we take a equals 1. And we do have to take a equals positive 1 this time because of the odd exponent. Negative 1 won't work. So if we'll plug in a equals 1 to this formula, we get x cubed plus 1 equals x plus 1 times x squared minus 1 times x plus 1 squared. So we get this. So in fact, the x cubed plus 1 stuff is not prime. It can be factored into this product. So the original polynomial, having already been written as x cubed plus 1 times x plus 1, can be further factored by factoring the x cubed plus 1 into x plus 1 times x squared minus x plus 1. And there we have a product of 3 prime things. Ooh, these first and last ones, these are the same. We can actually combine those as an x plus 1 quantity squared. What was that? This is prime. You can't factor x squared minus x plus 1. First off, the setting for us is factoring over the integers. If this did factor, then we could find integers a and b such that the product equals 1, capital C is what we have here, and the sum equals negative 1, the coefficient here, capital B is what we called it in the notes previously. But there are no integers, a, b, such that a times b equals 1 and a plus b equals negative 1. The only thing we could choose integers wise is 1 and 1 or negative 1 and negative 1, and neither of those pairs makes this true. So that's the reason this is prime over the integers. Maybe it factors somewhere else. It definitely factors over the complex numbers, but it doesn't factor over the integers, and that's our conversation here. So here we've got this written as a product of powers of prime factors. Now let's try something a little more general. So now we're going to consider a polynomial capital A, x squared, plus capital BX, plus capital C, where we take A not to be 1. If A equals 1, we did this upstairs. We did 1x squared plus capital BX plus capital C. We already had that, so we're extending it beyond the A equals 1 case. Here's what we'll do. Find the value of A times C. Multiply these two together. Find integers with a product of A times C that add up to give capital B. So it's similar to the previous technique, except instead of wanting the product to equal this, when we had a 1 here, we want the product to equal capital A times capital C. Okay. That is, symbolically, find integers lowercase a and b such that A times B, lowercase a, lowercase b, equals capital A, capital C, and their sum, lowercase a plus b, equals capital B. So this time we want the product to equal the product of these two, and we want the sum to equal this thing. In that case, that allows us to rewrite ax squared, capital AX squared plus capital BX plus capital C can be written as capital AX squared plus lowercase ax plus lowercase bx plus c. Remember, we said a plus b equals capital B, so these combine to give us capital BX, which we've got on the left-hand side. Not only that, but we're going to have a situation where we can factor this by grouping. We'll have a common factor between these two terms and a common factor between these two terms. And that'll allow us to factor, and certainly factor an x out of this, but some other things will happen, allow us to factor and deal with this by grouping. Now, all we're doing is factoring a second degree polynomial on this, but this will allow us to accomplish that. Let's look at two examples of that. Factor completely 8x squared plus 6x minus 2, if it can be done. Okay, how about we factor 2 out? Can't argue with that. It makes the number smaller than we have to deal with as well. So now we'll concentrate on the stuff in parentheses. So we've got an ax squared, capital AX squared plus capital BX plus capital C equals this stuff in parentheses, giving us capital A is 4, capital B is 3, capital C is -1. We were just told, look at the product A times C. This times that, 4 times -1. So we'll take capital A times capital C. 4 times -1 is -4. So we're looking for integers, lowercase a and lowercase b, such that the product of the lowercase letters equals this thing, which is -4, and the sum of the lowercase letters equals capital B. Capital B is 3, equals 3. So now we focus our attention simply on this little problem here. Find integers a and b that satisfy these two conditions. What is it that multiplies together to give -4? Well, 1 and -4, -1 and +4, 2 and -2, or -2 and 2, same thing. So there's only 3 cases there to go through. My hint is, consider this first. Of that collection of numbers, do any of them sum to 3? Yeah. If we take a equals 4 and b equals -1, of course, we could interchange those two. In this case, when you add these two together, we get 3. The product of these two is -4 as required. The sum is +3 as required. Let's use those numbers. So this gives the given polynomial with the capital letters, as we had in the notes, rewritten in terms of some of the lowercase letters. We've taken the b and split it into these two pieces. Then gives us capital A. What we started with was, for this polynomial, how about this, is 4x squared. We took the 3x and wrote it as plus 4x minus x, a and b. 4x minus x is indeed 3x. Here's the minus 1, the plus capital C thing over here. And look at this. They got the same coefficients. So we can factor a 4x out of this. I guess we could factor a -1 out of that. Let's do both of those. Factoring a 4x out leaves us with an x plus 1. 4x times x is 4x squared, correct. 4x times 1 is 4x, correct. So this can be factored, factoring out the 4x to give this term here. We want to factor that second term. Let's bring the negative out. -1 is the only factor we have to deal with. It could be more complicated than that. It's the b term that led us to that -1, but factor that out as well. Now you have a common term of x plus 1. Factor that out, leaving a 4x from this piece, a -1 from this piece to produce 4x minus 1 times the common factor x plus 1. Distribute back and you'll see that this is true. So now we factored, and so these are first degree polynomials. We can't factor constants out or anything like that. They're prime. So we've written the given polynomial as 2, don't forget the 2 that we started with, we threw aside to start with, times this, times that, times 4x minus 1, and times x plus 1. Completely factored, second degree polynomial, there you go. Having it completely factored, we could do some other stuff to that polynomial, like figure out where the polynomial is 0. This is one of the applications of this stuff. Let's look at another one. Factor x to the 4th minus 1 completely. If it can't be factored, say it can't be factored. Okay, this is maybe it's two problems for the price of 1 or something like that. You know what? That's a difference of 2 perfect squares. We had our formula for the difference of 2 squares. Okay, granted there's a 4 there, but we could treat this as x squared squared minus 1 squared. X squared squared is x to the 4th. Add exponents. We looked at that in Appendix A1. And let's take the 1 and write it as 1 squared. So x to the 4th minus 1 can be interpreted as a difference of 2 perfect squares. The square of x squared and the square of 1. So we can factor it. We had a formula that said difference of 2 squares can be factored like this. Okay, I'm using the same letters we were given in the formulas and in the exercise, but we don't have x squared. We've got x squared squared. So I'm taking this little x here covered up with a hand and replacing it with a big old x squared here, trying to cover it up with a hand. In other words, the x here is playing the role x squared over here. So we'll take this x squared and plug it in there and there and there, leading us to the factors x squared minus 1 times x squared plus 1 equals x to the 4th minus 1. If you don't buy it, pause and think about it. Pause the video and think it through. It's simply a substitution of x squared here for x in these 3 locations. You can substitute anything you want to for x. I want to substitute x squared. And for a, we're substituting 1. And that produces this. Multiply it out. FOIL this. Sure enough, you'll see you get x to the 4th minus 1. So this is accurate. So we've taken the original polynomial and factored it as this. But wait, x squared minus 1. That's also a difference of 2 squares. That one's easier. That's x minus 1 times x plus 1. I think we dealt with it earlier. So the x squared minus 1 factors into this product. So at this stage, we have x to the 4th minus 1 written as x squared minus 1 times x squared plus 1. And then we went further and factored this into x minus 1 times x plus 1, giving this product of 3 things. What's up with x squared plus 1? Can you factor that? No. We had a theorem that told us that x squared plus a squared was always prime. So this can't be factored. This is a prime factor. So we've got a complete factoring then over the integers at least, of x to the fourth minus 1 as this product of three things. The last topic is completing the square, which comes to us pretty unmotivated at this stage. We'll use this to derive the quadratic equation. So there's just some motivation right there. But for now, it's just an algebraic technique, algebraic trick. Why you would want to do this? Well, sit tight. We'll explain why when we do the quadratic equation. The idea behind completing the square is to take an expression of the form x squared plus bx, so an x squared term and an x term, coefficients 1 of the x squared, coefficient of the x could be anything, and there's no constants involved, and adding just the right thing to make it a perfect square. Notice if we had x squared plus 2ax plus a squared, that's x plus a squared. We had a formula for that. That was one of the few I said you probably ought to remember this one. Multiply the x plus a out times itself, FOIL it, and indeed this is what you'll get. Similarly, if we take x minus a and square it, we get this. So I'm trying to correlate this perfect square with this stuff here. We've got x squared plus something x. Well, here you got x squared plus something x, and you get a perfect square by adding the right thing. And here you've got x squared plus something x. The something carries a negative sign with it, but you also get a perfect square. So if the expression x squared plus something x, bx, we could treat this as letting b, or replacing b, or thinking of b as either 2a or negative 2a, maybe depending on the sign of it. Then what we need to add is this. Actually, it's the same on both sides. We'd need to add a squared. But if we have b acting as plus or minus 2a, we're going to do some squaring, so the negative signs will get absorbed. We need to take a squared then equals plus or minus b divided by 2, taking b equals plus or minus 2a, dividing by 2, producing a equals plus or minus b over 2, and then squaring both sides. The positive, the negativeness, the ambiguity is gone because the squaring will make it positive. And we're left with b over 2 squared. So what we'll do is take an expression of the form x squared plus bx and add just the right thing. The right thing to add is b over 2 squared. This then factors as x plus b over 2 squared. Multiply it out, you'll see it happen. If we take x squared minus bx and add just the right thing, it's the same thing, b over 2 squared. You'll get a perfect square as well. Why you want to get a perfect square? Well, granted, unmotivated now. The real reason is so we can do the quadratic equation. For now, just the manipulations on completing the square. So you'll be given something of this form, and you'll add just the right thing, or with a negative sign in it, something of this form. You'll add just the right thing. And by doing that, you'll be guaranteed to get a perfect square. As an example, final one from this section, let's look at number 126. Determine the number that should be added to complete the square of the expression p squared plus 14p. Then factor the expression, write it as that perfect square. So they've given us p as the variable instead of x. So maybe that's the first time we've seen that kind of thing in the appendices. So that's exactly of the right form. It's of the form x squared plus bx, except they use p's. The leading coefficient is 1, and we've got b equals 14 in this case. We know these to be equal to each other by the notes. So we've got b equals 14, and we want to add this. We want to add 14 divided by 2 squared. 14 divided by 2 squared. 14 divided by 2 is 7. Square it, get 49. We want to add 49. So if you'll take p squared plus 14p plus 49, then you'll get a perfect square. I can even tell you what it is. It's x plus b over, I'm sorry, it's for us, p plus b over 2. P plus 14 over 2. P plus 14 over 2, quantity squared. Well, 14 over 2 is 7. It's p plus 7 over 2. Excuse me, p plus 7 squared. FOIL this out, you'll get the first one squared, p squared, right? You'll get the last one squared, 7 squared is 49, right? And you'll get twice the product. Product is 7p, twice that's 14p, right? So there's the technique for completing the square. Again, our motivation for doing this, completing the square stuff, is really to do the quadratic equation. Our big motivation for doing this factoring is so we can find zeros of polynomials, it turns out. And the best way to find the zeros of a second degree polynomial, well, the best way is to factor it, but if you can't factor it, there's still the quadratic equation. If the zeros are integers, then it can be factored, and with the techniques that we've seen in this appendix. If the zeros are more complicated, it might take something else. If they're complex, it's probably going to take the quadratic equation in this class for us to find them. But we'll ignore complex zeros, but we still need the quadratic equation. And that takes care of this appendix. So we'll do a little bit more algebra from the appendices, and I'll see you soon in the next video and the next algebraic topic. Have a nice day. Bye-bye.